Let's discuss a question from machine design. 80 mm diameter cylinder shaft is subject to bending movement and twisting movement. So you have a shaft. Okay, so now it is subjected to the bending movement as well as the twisting movement. Okay, so M is the bending moment, that is given as 2.5 kilonewton meter. So that is the thing. So I'll convert into Newton and mm. So kilonewton is 10 power 3, meter into mm is 10 power 3. So that will become 10 power 6 Newton mm. Okay, the twisting moment is also 4.2. So going by that logic, it is 4.2 into 10 power 6 Newton mm. Okay, so now the if you look at the critical point in this, due to the bending movement at the top, if you look at any cross section at the top, there'll be the maximum shear stress, and due to the maximum normal stress, and due to the torque there'll be on the periphery there'll be a maximum shear stress. So if you combine these two and if you take a small element here, so on this element the maximum principal stress due to bending is given by, because it's a circular shaft, so I'll directly write down 32 pi by d cube. Otherwise the way you get it is m by I sigma by y, and y is for the circular section area moment of cross section pi d power 4 by 64, and y is d by 2. So that is the way you get it this. So that is from the bending beam equation, as well as from the torque beam equation, from the torque equation T by J tau by R, where J is polar momentum inertia of the cross section, pi d power 4 by 32, and R is d by 2. You get the maximum shear stress. So this is the polar, the twist of the shaft. The shear stress is due to the twisting moment of the shaft is given by this, and this is the bending equation. So these two are used and to find out this sigma 1. So this is the sigma 1. Now the shear stress which is due to the twisting is, along with the complement, is given like this, and this tau value is 16 T by pi d cube. So these are the formulas, these are basic formulas for cross section, circular cross section. Otherwise the formulas will change. You have to derive from these two. Okay, so once we got this, now what is we are asked to find out the factor of safety with respect to maximum shear stress theory. The maximum shear stress theory says that tau max is equal, should be less than or equal to your tau y. Okay, for the safe side. And in terms of factor of safety, tau max is equal to tau y by factor of safety. So the factor of safety is how much times your yield stress with respect to the shear stress at the yield to the shear stress in the critical point. So now tau y is the sigma naught by 2, that is the yield by 2, as well as tau max is the max principal stress minus the mean principal stress by 2. Max and the mean I am denoting by 1 and 3. Now in this state, what is our max and what is mean? Now let me write here max, because one you may confuse with this max and min. How do you find out max and min? So the max principal stress for a 2D state of stress, something like this, it's given as sigma 1 plus sigma 2 by 2 plus or minus, so that will cover both max and mean, sigma 1 minus sigma 2 whole square by 4 plus tau whole square. So this covers everything. Okay, sigma 1 minus sigma 2 square by 4, or sigma 1 minus sigma 2 by 2 whole square. Okay, so now obviously the tau max is given as the difference of the maximum principal stress minus minimum principal stress by 2. This is from the Mohr circle also, you can say. Okay, so if you divide that, it will be basically becoming sigma 1 minus sigma 2 by 2 whole square plus tau square. That is my tau max. Okay, that is my tau max. Now there is no sigma 2, because sigma 2 is 0, we have only sigma 1, so it becomes sigma 1 by 2 whole square plus tau square. And if you want to convert in terms of bending movement, so and So then it becomes 16 m by pi d cube whole square plus 16 t by pi d cube whole square. So 16 by pi d cube we can take out common from this, so it will be root m square plus t square. So this is what is my tau max. So if I substitute that here and if I come back here, my factor of safety will be basically, so sigma naught by 2 is at the top and this is the tau max. So basically I am using this equation and tau max is this, so I'll be using 16 by pi d cube root m square plus t square. Okay, so now is the time we have to solve it. So we got FOS to be, I've just erased that part, and FOS to be sigma naught by 2 by 16 by pi d cube root m square plus t square. This is what we got in the last thing. So this will become, let's substitute it. What is the given? Sigma naught is given, the yield stress of the shaft is 300, 2 is 2, 16, pi d cube comes in the numerator, so pi, or if you want to have pi d cube, which is 80. Everything dimensions we are substituting in mm, forces in Newton, so that stresses you get in MPa. 16 by 1 pi d cube I have taken that side, to m square plus mt square. Now that is already 2.5 into 10 power 6 whole square. It's in Newton per mm square, which at the start we have seen this, and 10 power 6 whole square. So this is one big equation, and if you try to solve this, you get a, if you just compute this is 3.08, close to 3.1. So this is a big problem, but it covers the entire bending and twisting of the shaft. So A is the answer. This is a good problem. Practice it.